Good afternoon, welcome to EduSat Network. Friend, as you know, this week we have lecture on chemistry and the precise topic is spectroscopy. In the previous lecture we talked about fundamentals of a spectroscopy, and then we talked about atomic spectra in detail, and now we move further and we'll talk about molecular spectra. There are different subsections of molecular spectra: rotational spectra, vibrational spectra and electronic spectra. But today we'll focus only on rotational spectra, and if we have time we'll move further and we'll have discussion in detail. And for discussion on this very topic we have in the studio Dr. Rita Kakkar. She teaches chemistry in Delhi University and her area of specialization is spectroscopy. So I welcome her and request her to start the lecture. Welcome.
Thank you. Welcome viewers. And today we have already finished atomic spectroscopy, and I gave you a little brief background also about line broadening and other aspects. Today we will be moving into the first topic from molecular spectroscopy, and basically what contents of a spectroscopy course could be the study of electromagnetic radiation, quantum theory, interaction with matter and so on, that we discussed in the first lecture. Then comes atomic spectroscopy, and as I said, in some of the books atomic spectroscopy is discussed along with electronic UV visible spectroscopy, but here I have not discussed it there because atomic spectroscopy is slightly different from other forms of spectroscopy, being only electronic in nature. Then we have rotational spectroscopy, which is the first topic that we are going to take up in molecular spectra. It has a lot of resemblance also to atomic spectroscopy because here also we are dealing with angular momentum. Then there are other forms of molecular spectroscopy like vibrational spectroscopy, Raman, which is also vibrational Raman, vibrational rotational Raman. Then UV visible spectroscopy of diatomic molecules is normally discussed differently from that of polyatomic molecules, and generally we also have NMR spectroscopy, Moss-Bohr. There are so many fields depending upon the time available. Different universities will have different syllabi. Now, before we move over to this branch of spectroscopy, the molecular spectroscopy, let us see how molecules are different from atoms. While the atoms can only have electronic energy, molecules can also vibrate and they can also rotate, and obviously they also have electronic energy levels. So besides the electronic energy levels, they also have vibrational energy and rotational energy. The electronic transitions are generally observed in the visible and the ultraviolet region. Vibrational transitions, they are in the infrared region, and rotational transitions are in the microwave region or radio wave region, and because they have the lowest energy, this is what we are going to discuss first. And also I told you that it has some resemblance to what we learned in atomic spectroscopy, so this is what we are going to learn. So that means a molecule can have three different kinds of energy. It can have electronic energy, it can have vibrational energy, it can also have rotational energy. According to the Born-Oppenheimer approximation, you can treat them independently of each other. When we look closely at molecular spectroscopy, we find that they are actually not independent, because rotation, if a molecule is moving faster, its bond length will increase because of the centrifugal force, it will affect the vibration of the molecule. Similarly, the electronic energy also will be affected by vibrational and rotational energy. But according to the Born-Oppenheimer approximation, we can take them as separate, because the electronic energy levels have a huge spacing of around 25,000 centimeter inverse. Vibrational energies have a spacing of 1000 centimeter inverse, and rotational transitions only have a spacing of 1 to 10 centimeter inverse. So because of the large difference between the different energies, we normally treat them as independent of each other as a first approximation, and later on see what is the effect of each on the other one, which I am not going to take it up in this particular course. Now, obviously, because the electronic transitions take place in the high energy UV and visible region, they are classified separately from vibrational transitions which take place in the lower energy infrared region, while rotational energies lie in the lowest energy microwave region, and that is why there is actually a segregation of the three types. We divide the study to electronic spectroscopy separately from vibration rotation spectroscopy and then pure rotational spectroscopy. In the microwave region, the molecule only has enough energy to undergo rotations. Since if you supply only 1 to 10 centimeter inverse of energy, there is not enough energy for a vibrational transition which requires at least 1000 centimeter inverse to take place. And similarly, when you are studying in the infrared region, there is no chance of an electronic transition also taking place. But while an electronic transition is taking place, simultaneously vibrational transition, vibrational rotation and rotational transitions can take place. And because of this, we generally first study pure rotational spectroscopy because there is no complication of vibration. Then we study pure vibration spectroscopy, see the effect of rotations on the pure vibration spectroscopy, and then finally when we study electronic spectroscopy, we study the effect of vibrational energy change and the effect of rotational energy change. So this is the hierarchy, the way we study molecular spectroscopy. We start with pure rotational spectroscopy in the microwave region, then move on to vibration spectroscopy and then vibration rotation spectroscopy in the infrared region, and finally to electronic spectroscopy in the visible and UV region. Now molecules can vibrate and rotate besides having electronic energy, and this is how do we separate the various energy levels for a molecule? The electronic transition, as we see, has the highest energy, around 25,000 centimeter inverse. Each electronic state, for example, you have a ground state, the lower energy state, and the excited state, which is an excited electronic state. Each one of them has its own vibrational energy levels. So while an electronic transition takes place, a vibrational transition is also possible. Each vibrational level also has its own rotational energy levels because they have smaller spacing, and the total energy is given by electronic energy plus vibrational energy plus rotational energy plus translational energy. I did not speak about the translational energy in the last when I was discussing in the last slide, because translational energy is actually not quantized, because we are talking about molecules in large containers, and we know that quantum theory does not apply. The energy levels are almost continuous, the spacing is almost zero, so you cannot study the spectroscopy, translational spectroscopy, and that is why we do not have any kind of translational spectroscopy. And the energy levels are arranged like this: the electronic energy differences are largest, followed by vibration, followed by rotation, and followed by translation. And this is how you can draw an energy level diagram. Suppose E is the ground, E naught is the ground state, and E prime is the excited state. The ground state has its own vibrational energies, which is a fine structure, and every vibrational level has its own rotational levels, which we can call the hyperfine structure. And so every electronic energy level has its own set of vibrational energy levels, and every vibrational level has its own set of rotational energy levels. Now the regions of the electromagnetic spectrum are like this, starting from the lowest energy region, which is the radio waves on the right, and then going on to microwaves, infrared, visible light, and visible, then ultraviolet light, then X-rays, gamma rays, and cosmic rays. This is how the energy levels change. In the radio wave, you study the NMR spectra, because in NMR spectroscopy we study the effect of spin transitions of the nuclei, and because of that the energy levels are so small, the difference in energy levels is so small that it occurs in the radio waves. The next is microwave region, where we know that rotational transitions take place, and also electron spin flipping also takes place in this region. And then we have the infrared region. The visible light is what we are most familiar with, the colored light that we see, the white light which can be split into different colors. But beyond that, at lower energy you have the infrared, which is beyond the red. It has lower energy than the red part of the visible spectrum, and here we study vibration. The energy is just sufficient to cause vibrational transitions to make the molecule vibrate faster. On the other side of the violet region you have the high energy ultraviolet radiation, and both electronic transitions take place both in the ultraviolet region and also in the visible region, and that is why the electronic spectroscopy is studied in these two regions. Then we have the X-ray region, which in the X-ray region you are able to cause excitation of the core electrons. Remember, when we were writing down the atomic states, we did not bother about the inner electrons like the 1s2, 2s2. We said that they are the core electrons, they do not participate in any kind of bonding. Now, they are very close to the nucleus, and so their electronic energy is very, very negative. To cause transitions in these requires more energy, and X-rays have enough energy to cause this. X-rays cause other kinds of transitions also, scattering, photoelectron and so on, but we will not worry about these right now. Then we have the gamma rays where nuclear transitions take place, and the cosmic rays where even higher energy transitions take place. So we have different regions of the electromagnetic spectrum, and depending on the different regions of the electromagnetic spectrum, we have different kinds of spectroscopy that we study. And as I have been saying, pure rotational spectroscopy, which is uncomplicated by vibrational or electronic spectroscopy, is studied in the microwave region. It is also called microwave spectroscopy. Any kind of transition is caused by the interaction of electromagnetic radiation with matter. In this case, what is that in the matter that causes transitions to take place? For the electromagnetic radiation, it is the oscillating field, electric field, that causes the transitions. We have already seen that electromagnetic radiation has an electrical field and a magnetic field perpendicular to the direction of propagation, but the magnetic field interaction with matter is very small, so we do not bother about it. But the interaction of the electric field causes the transitions which could take place in microwave spectroscopy or infrared spectroscopy and so on. If a molecule has a dipole moment, then the electric field can cause a transition, and it can cause it to rotate faster by increasing its rotational energies. That means that a fundamental condition, the first selection rule that we have, the cardinal selection rule, is that the molecule should have a permanent dipole moment for it to show a pure rotational spectrum. If it does not have a dipole moment, in that case it will not show pure rotational spectrum. Since rotational spectroscopy gives us information about the molecular structure, we cannot obtain molecular structure information for molecules which do not have a permanent dipole moment from microwave spectroscopy. There are other ways of finding it that we will discuss later on, but microwave spectroscopy cannot be studied. This means that all the homonuclear diatomic molecules, hydrogen molecule, N2 molecule, nitrogen, oxygen, fluorine, none of these is microwave active. This is how we say that it is not microwave active, means it cannot interact with radiation in the microwave region. They should have a permanent dipole moment. While carbon monoxide, which is a heteronuclear diatomic molecule, will show microwave spectrum. We say it is microwave active. Nitric oxide is also microwave active because it is the NO molecule. HF, HCl, all of these are microwave active molecules. And one fallout of this is that when a microwave signal passes through air, it does not get depleted because it is passing through air which contains mostly nitrogen and oxygen and other gases like carbon dioxide, which also does not have a dipole moment because it is a symmetrical molecule. So the signal does not get depleted, and that is the reason that in radars microwave radiation was being used. It is also microwaves is the radiation that is also used in cell phones and so on, and because it travels through air, it does not get depleted when it travels through the air. The microwave spectrum also has applications in the microwave cookers and so on that we know about, but right now we will talk about how spectroscopy of microwave in the microwave region and pure rotational spectra. Now, suppose a molecule has a dipole moment, then there will be a rotation is possible, and when rotation takes place about the center of mass, the dipole moment component keeps on changing, because suppose the molecule is like this, it does not have any dipole moment component in the vertical direction, but suppose it goes like this, then it has the dipole moment component in the y direction, and this keeps on changing. It goes from a maximum, the Please show this. The figure in the at the bottom shows how it keeps on varying. While the molecule is going on rotating, the field of the component of the dipole moment keeps on varying. And if this matches with the frequency of the electromagnetic radiation, then transition can take place and the molecule can become excited in the microwave region, rotationally excited, and that is why molecules which have a dipole moment have pure rotational spectra. The wave numbers at which this occurs is around 0.1 to 100 centimeter inverse, very low, and this is in the microwave and far infrared also. There is actually no region where you can say that microwave spectroscopy will show pure rotational spectrum and IR will show pure vibration. There are in between regions like the far infrared region where some of the molecules, for example, molecules which are hydrogen halides, any molecule containing hydrogen will probably show a spectrum in the far infrared than in the microwave region, and there is a reason for it that we will know right now. Now, suppose you consider a mass that it is rotating about. There is a mass which is rotating in a circular direction and the radius of the orbit is r about the center. If theta is the angle which it makes with the x axis, this angle keeps on changing with a velocity which is given by omega, which is the angular velocity. D theta by t is the angular velocity which is measured in radians per second. The tangent to this is the linear velocity which is given by r d theta by dt or r omega. So, the kinetic energy, which is half mv square, as we know, the rotational kinetic energy is given by half mr square omega square that we have all applied from this. Now, if the molecule has several atoms which are all rotating about the center of mass, then the total rotational energy or the kinetic energy, rotational energy is only kinetic energy, no potential energy, because the atoms are not changing their distance with respect to each other. So, there is only kinetic energy, and the total kinetic energy is given by the rotational kinetic energy is given by half m1 r1 square omega square plus half m2 r2 square omega square, and this keeps on, you keep on adding all the masses that are moving. And notice one thing, that omega is a constant because the angular velocity will be the same for all the atoms that are moving in a particular rotation. And so, the total energy of rotation can also be written as summation mi ri square omega square, and as we know, summation mi ri square is the moment of inertia of the molecule. So, it is given by half I omega square, where I is the moment of inertia of the molecule. Now, if you look at this, you see that it has resemblance to the half mv square kind of relation that you have for linear velocity. If you replace m by the moment of inertia and v by the angular velocity, then you get the kinetic energy of rotation. There is a similarity between this angular kind of motion and the rotational kind of motion and the linear velocity. Now, for the purpose of understanding the spectra, the molecules are divided into different classes. How are they divided into different classes? Suppose it is slightly complicated, but I will try to explain. Suppose we plot the moment of inertia, we calculate the moment of inertia in different directions and then plot 1 by square root of I in the different directions. The figure that we get will be an ellipsoid. Wherever the moment of inertia is small, the ellipsoid will have its major axis, and wherever it is large, it will have the minor axis. The reason being that we are plotting 1 by square root of I. So, if I is large, in that case the ellipsoid will have its minor axis. So, you get a 3-dimensional figure. Depending upon the shape of this 3D figure, we classify the molecules into different categories. Here I am going to talk only about one category of molecules, but we must know that there are other categories also. The first category is where a molecule is spherically symmetrical. For example, the methane molecule, which has tetrahedral symmetry, it is a spherically symmetrical molecule, and for a spherically symmetrical molecule, the moments of inertia about the 3 axes Ia is equal to Ib is equal to Ic, they all have the same value, and such a molecule is called a spherical top molecule. Examples are all molecules with octahedral symmetry, all molecules with tetrahedral symmetry, like carbon tetrachloride, SF6, sulfur tetrafluoride, sulfur hexafluoride, all of them have are spherical tops. The reason the spectra of these molecules is of no importance for us is that they do not have a dipole moment. Because of their symmetry, they do not have a dipole moment, and so they are microwave inactive. We cannot study their spectra in the microwave region, but we must know that this is a classification. The next classification is for the linear molecules. The linear molecules have three, like any other kind of molecules, they have three moments of inertia, but one of these is equal to 0. Now, the moment of inertia measures how difficult it is to rotate the molecule about an axis. Suppose I look at this axis. If I look at this axis and rotate the molecule, this is the internuclear axis. I could be looking at a molecule like carbon monoxide, one end is carbon, the other is oxygen. If it rotates like that, the nuclei are not changing their position, they are just rotating about the axis. This rotation is the easiest, there is no moment of inertia for this, and this moment of inertia is equal to 0. Whereas rotation perpendicular to this axis, this could be IB, this has a moment of inertia, and similarly another direction is this one, where also the moment of inertia is the same as what we got for this one. So, it has three moments of inertia, one of these is equal to 0, the other two are equal to each other. By convention, the smallest one is labeled IA, the next larger one is called IB, and the third one is called IC. So, in this case, we will write down IA is equal to 0 and IB is equal to IC. Example molecules could be carbon monoxide, carbon dioxide, any molecule which has which is a linear molecule, acetylene, any linear molecule will be classified like this. So, for linear molecules, you have two axes of rotation about which the moments of inertia are the same, and one axis of rotation is equal to 0. And you will recall that when we talk about the degrees of freedom of a molecule, for linear molecules we say it has only two rotational degrees of freedom, because rotation about the bond axis is not a rotation, it actually becomes a vibration. Then we have the next class of molecules, in fact probably the most important class of molecules, which are called symmetric tops. For these molecules, two of the axes have the same value and the third one has a different value. One example is CH3Cl. Now, in CH3Cl, along the CCl axis, if you look at the moment of inertia, only the hydrogens are perpendicular to that axis and they will be contributing to the moment of inertia. Since hydrogen, remember that the moment of inertia is equal to summation mi Ri square, where Ri is the perpendicular distance of the atom from the axis that we are talking about. Now, only the hydrogen atoms will be contributing to this, and because they have a lower mass, they will have the moment of inertia about the CCl axis is very small, whereas the moment of inertia about the other two mutually perpendicular axes will be larger and it will be equal to each other because of symmetry. For a linear molecule, all the atoms lie along the axis, so the perpendicular distance is equal to 0, so Ia was equal to 0. Here Ia is not equal to 0, but it has a finite value, but it is smaller than Ib, which is equal to Ic. Such kind of molecules like carbon tetrachloride, which has a chlorine here, C here and hydrogens like this, looks like a shuttlecock, the instrument with which you play badminton. It has the same shape. All molecules which have Ia less than Ib equal to Ic, Ia, the third axis, has the smaller moment of inertia and the other two are the same. These are called subdivided into the spherical tops as prolate symmetric top molecules. Such molecules are called prolate symmetric top molecules. Another category is the oblate type molecules, in which the moment of inertia which is different from the other two is Ic. That means that the third moment of inertia is larger than the ones which are equal. In this category of molecules, you have flat molecules which look like a saucer or discus or anything of this sort. Examples are all planar molecules like benzene. Then you have molecules like BF3, a planar molecule like BF3. Any other planar molecule will be classified as a symmetric top, but within that category as an oblate symmetric top. Then you have the asymmetric top kind of molecules where all the three moments of inertia are different. Now, it is difficult to understand the spectra, but usually they will belong to they will be closer to either the symmetric top prolate or to oblate, and we try to interpret them in the spectra in terms of the symmetric tops, whichever they are closer to. Either we call them as near prolate or near oblate. So the asymmetric top molecules have Ia equal to not equal to Ib, not equal to Ic, and molecules like water, where the highest axis of symmetry is C2, are classified in this species. They have very complex spectra, and example is water, SO2, any molecule where the highest order axis is smaller than threefold axis. Now let us first start with diatomic molecules. Like I said, for atomic spectra, in any class of spectroscopy or in quantum mechanics, it is always convenient to first express the energy in terms of the classical expression and then write down the quantum mechanical expression and then see what happens to the energy levels, how they get quantized. In this case, we had observed that for a diatomic molecule, the I is simply equal to mu r square, where mu is the reduced mass. If you substitute the expression, we got m1 r square plus m2 r square and so on about the center of mass, m1 r1 square omega square plus m2 r2 square omega square. It finally becomes I is equal to mu r square, where r is the internuclear distance. You have a smaller mass and a larger mass, and mu is known as the reduced mass, and it is given by 1 by mu is equal to 1 by m1 plus 1 by m2, which when you rearrange becomes equal to mu is equal to m1 m2 divided by m1 plus m2. So now I come to a very important aspect. Since 1 by mu is equal to 1 by m1 plus 1 by m2, if you have a hydrogen halide, for example HCl, then 1 by m1, if m1 is the mass of the hydrogen, will be larger than 1 by m2 if that is the mass of chlorine, because chlorine is much heavier than 36 times heavier than the hydrogen atom. So 1 by mu would approximately be equal to 1 by h, and that means the mass will be the reduced mass will be that of the hydrogen atom, and it will be very, very small, and that is why the moment of inertia of such molecules is very large. Whenever you have a hydrogen atom, then the moment of inertia, because the mass is small, the moment of inertia is smaller for such molecules. Now diatomic molecules are characterized like this. For them Ia is equal to 0 and Ib is equal to Ic. A diatomic molecule can rotate around a vertical axis. The rotational energy is quantized. So when we write down the expression for the kinetic energy, I said that there is no potential energy in the case of rotation, because you are not stretching the bond, the internuclear distance is remaining the same, and about the center of mass there can be any kind of rotation about this center of mass. So now the next step is to write down the Schrodinger equation for this, and it is slightly complicated in the sense that now we are talking about a molecule which the center of we are talking about rotational kind of motion, and so we have to convert a Schrodinger equation from xyz coordinates to the spherical polar coordinates and then solve for the rigid rotator problem. We will not do that, we will just take the results of that, and the results are that the energy is quantized and is given by h square, where h is Planck's constant, divided by 8 pi square. I is the moment of inertia, pi is the usual pi, and j into j plus 1, where j is the rotational quantum number. The moment you solve the Schrodinger equation, you always get 1 or 2 quantum numbers depending upon the problem that you have in hand. Now in this particular case, the quantum number j is the rotational quantum number, and it can have values starting from 0, 1, 2, 3, any integer value starting from 0. And you will notice that unlike the case of a particle in a box, j can also have a value equal to 0, meaning that rotational energy can also be equal to 0, because j into j plus 1 in that case will be equal to 0. Now normally the energies are expressed, and because it is more convenient to use the wave number for these, so we divide by c, and the energies are expressed in units which are h by 8 pi square c I, j into j plus 1, we have just divided by E. The capital E divided by c, the speed of light, gives us the rotational energy. From joule it becomes equal to centimeter inverse, because we have divided by hc, and the energy from joules becomes centimeter inverse, and the whole h by 8 pi square IC is called the rotational constant, and it is given a symbol B and with a curly kind of top over it, and this is used to signify that we are expressing it in wave numbers. In my first lecture I said that wave number is a very convenient unit. In SI it should be expressed in meter inverse, but somehow the centimeter inverse has stuck because the values are very convenient to use in the centimeter inverse. Why do we call the rotational constant B, why not A or C? Because remember, for a diatomic molecule, B is equal to C and A is equal to 0 because the moment of inertia is equal to 0. There is no A rotational constant. This is equal to h by 8 pi square IC is given the symbol B, and this is the rotational constant, and it has a value equal to h by 8 pi square IC. Since we are in spectroscopy, what we have to do is we have to take the classical picture and then translate it to a Schrodinger equation, solve the Schrodinger equation, solve for all the quantum numbers and see how the rotational energies are available. Now, for any kind of spectroscopy, I said not all transitions are possible. The reason being that the interaction of radiation and matter requires certain conditions to be specified. Since when you are talking about rotation, you are talking about the angular momentum, it is angular rotation, and as we said, even in the case of atomic spectroscopy, there the J quantum number signified the total angular momentum. Here J does not specify the total angular momentum because there is no spin angular momentum in this case. J is the angular momentum which is analogous to the L quantum number that you had. What did we say for L? We said that L signifies the angular momentum. The photon has an angular momentum of 1 unit. So, if our molecule is absorbing a photon, its angular momentum should increase by 1 unit. Similarly, if it emits a photon, then its angular momentum should decrease by 1 unit. These two relations are combined in the statement that delta J is equal to plus minus 1. It can be rigorously derived, but we are not going to do it here. We will just take the result that delta J is equal to plus minus 1, and the fundamental selection rule is that the molecule should have a dipole moment. So, thus for the absorption spectrum, we can calculate the position of the lines by considering the energy change when J becomes equal to J plus 1. When an absorption transition takes place from a particular J value, then it goes on to J plus 1, and to find out what is the energy change for this transition, we find out the energy of the J plus 1 state by substituting J plus 1 for J in the expression B J into J plus 1 and subtracting the energy of the lower energy state, and what we find is that delta epsilon is equal to 2B J plus 1. This means that you will have lines corresponding to different values of J. At the first line will be at 2B bar, then for J is equal to 1 it will be at 4B bar, and when for J is equal to 2 it will be at 6B bar, and so on, because you are going on increasing it by 1 all the time. So, you get a sequence of lines at 2B bar, 4B bar, 6B bar, 8B bar, and what we find is that the separation of these lines is 2B bar, from which we can measure the rotational constant as the spacing between two rotational lines. Once we got the rotational constant, what else can we determine? This is something like the rotation spectrum of carbon monoxide that I will discuss just now. Remember that B is equal to h by 8 pi square IC. So, if you know the value of B, what you can determine is the value of the moment of inertia, because all the others are universal constant. H is the Planck's constant, pi square, C the speed of light, and so on. So, you can find out larger value of rotational constants mean that the moment of inertia is small. And now we understand that for moment of inertia for hydrogen halides, I said the moment of inertia is small because the mass of the hydrogen atom is small, and this means that the moment of inertia is small and B bar is large, and the separation 2B bar will go on into the not in the microwave region, it will go on to the infrared region, or at least the far infrared region, and normally for hydrogen halides the lines are observed in that region, but carbon monoxide and other molecules are observed in the microwave region. So, this is a rotational spectrum obtained for carbon monoxide, where we have plotted the transmission. either the absorption is the absorbance or the percent transmission is plotted against the wave number to get a spectrum. This is a spectrum. The first time we are seeing a spectrum, and it tells you that at different values which have almost equal spacing, what you find is that there is a dip, which means that the transmission has become small. Now, why has the transmission become small? The transmission has become small because the molecule has absorbed radiation, and that means that from the radiation that you supplied to the molecule, it has absorbed some and transmitted whatever remains, and the transmitted light is less, and that is why what you find is that at regular intervals you have peaks, reverse peaks. So, this is the rotational spectrum of carbon monoxide. If you measure the spacing between the different lines, it will give you the 2p bar value, from which you can find out the moment of inertia of the carbon monoxide molecule. Now, how can you use it? You can find out that the line spacing is equal to 3.84 centimeter inverse. I have not taken the complete value. In fact, in most of the books you will find that the value is reported up to the 6th place of decimal. The reason is that rotation gives us very accurate values of the rotational constant, which are correct up to the 5th or 6th place of decimal, even beyond that. And 2b bar, if it is equal to 3.84, this just for simplification we are using this. Therefore, b will be divided by 2, it will be 1 by 1.92, and if you find out the moment of inertia, this is equal to h divided by 8 pi square c. We have roughly taken as 3 into 10 raised to the power of 10 centimeter per second, because we want to express the result. We have got the wave number in centimeter inverse, and when you cross out all the remaining units, what you find is that the moment of inertia has turned out to be of the order of 10 raised to the power of minus 46 kg meter square. Now, what else can we determine for carbon monoxide? We found out the moment of inertia, and we know that it is equal to mu, the reduced mass, multiplied by r square. So, since we know the reduced mass of carbon monoxide, we have very accurate masses for the carbon and oxygen atom. What we do is, I am not doing it very accurately here, but it can be done very accurately. We take the mass of the hydrogen atom as 12 into 10 raised to the power of minus 3 kg, because 12 is the atomic mass in grams, and for the other atom it is oxygen, which has 16 into 10 raised to the power of minus 3. A rigorous calculation I should have used 15.9994, which is the exact mass for the oxygen atom. Divide by m1 plus m2, and you divide by the Avogadro's number, so that you get the mass in kg per molecule. We are not talking about a mole of the molecules, we are talking about the one molecule. So, we divide by the Avogadro's number, which is 6 into 10 raised to the power of 23, and what we finally observe is 1.138 into 10 raised to the power of minus 26 kg is the moment of inertia of the carbon monoxide molecule. But we also know that I is equal to mu r square. So, since we know the value of mu, we can easily calculate the value of r square, and from there we can find out the r value in meters. Here I have reported the value only up to 0.113 nanometer. Actually, the value can be reported to many more places of decimal. It is very accurate. It is one of the most rigorous techniques which gives you very accurate values. Now, this means that the line spacing from microwave rotational spectrum of a diatomic molecule, it allows us to get the bond length. What other things can we obtain? Since you get the moment of inertia, and the moment of inertia depends upon mu and r square, if you know the value of mu accurately, you can find out the r value, that is the internuclear distance, but if you know the value of r from any relation, then you can find out the mass of unknown atoms, and this is what I am going to illustrate just now. If you look at this spectrum, what you find is that there are in between, it is not regular. Look at the top end, there are small dips also. Now, what are these dips due to? You have a regular peak, and on the left there is also a smaller peak. Now, what is this small peak due to? This small peak is due to the other isotope of carbon 13CO, which is present in atmospheric carbon monoxide. Now, you do not even have to do another experiment. A spectrum of carbon monoxide, regular carbon monoxide, without doing any isotope enriching or anything, gives you a set of lines. You will also notice that they are to the left of each regular line. Carbon monoxide with the 12 carbon has a smaller moment of inertia as compared to the 13 carbon O. So, because it has a larger mass, carbon 13 has a larger mass, so the mu value is large. That means its moment of inertia of carbon monoxide, the 13CO, is larger because of its larger mass, and that means its B value is smaller, and that is why it is coming to the left at smaller wave numbers as compared to the regular peak. Now, the interesting thing is that you do not need to do any other special experiment for this. The natural abundance of the isotope is enough. We did not take any enriched sample of carbon monoxide. We just took the normal sample of carbon monoxide, which already contained some amount of the 13C isotope. Now from the difference, by taking the ratio of the peaks, what you can also determine is what is the natural abundance of 13 carbon oxygen as compared to the 12 CO, because the peak is larger for 12 CO because that is in larger amount. The intensity from 13 CO is smaller because it is available in smaller amount. So, the ratio of the peak heights can give us some idea about the natural abundance. Now, what we assume here is that there is only a change in mass, and because of that there is a change in the moment of inertia, and there is a change in the B bar value. We are assuming that the R value, the internuclear distance, is independent of isotopic substitution. It is a good approximation but not very accurate, because if you change the mass of an atom, the internuclear bond distance also does change, but by a small amount. So, as a first approximation we take it as unchanged. Now, you have seen on the top axis we have shown the expected lines of the peaks for 13CO, and these you can see are clearly seen in the spectrum, and the natural abundance of carbon 13 is 1.1%. Still you are able to, such a small natural abundance, still you are able to see. Now, what about the intensities? We find that the intensities are also varying with the rotational quantum number, because all these transitions that we are seeing are probably j is equal to 0 to 1, then 1 to 2 transition, then 2 to 3 and so on, all these transitions, because remember that the selection rule is delta j is equal to plus minus 1. So, because all these transitions are from different quantum numbers, we can see that some of the transitions have higher peaks and some of them have lower peaks. Now, what is the reason for that? The intensity in this case depends on two factors. One is the Boltzmann distribution, which depends upon the temperature. We have already discussed it in the last lecture where we talked about the Boltzmann distribution, how it affects the population. Suppose you take N1 by N0, and we know that it is according to the Maxwell-Boltzmann distribution law. It depends upon exponential minus Ej by kT, actually minus delta Ej by kT, but the energy of the 0th energy level is 0. So, Ej minus 0 is Ej only. So, I have written it like this, and this is equal to BHC. If you are writing down the actually it is B bar HC, j into j plus 1 divided by kT, where we have written B divided by HC is B bar multiplied by HC, and this is equal to, by putting in all the values of this constant, all of these are constants, HC by K, the value that we get is dependent upon the J value and on the temperature. But suppose we find out the value of N1 by N0, because the rotational energies are so close to each other, we find that the value is almost equal to 1. But for higher values of Nj, obviously the population keeps on decreasing exponentially, and for very high values of J, the population will become very small. But for the initial few energy levels, the population is almost the same due to the Boltzmann distribution, because the energy levels, remember that we are putting all these values, if B is very small, the exponential decay is very small, that means that N1 and N0 have almost the same population. Now, the second factor that we have to talk about is degeneracy. Remember that J is also a quantum number, and it is analogous to your L quantum number, and because it is analogous to the L quantum number, its degeneracy is equal to 2J plus 1. That means there are 2J plus 1 values of Mj, as I have shown in the lower figure. For an Mj equal to 2, the values are 0, 1, 2, -1, -2, just like you have the L quantum number. Now, in the absence of the external field, they are all degenerate, and that means that the degeneracy value is equal to 2j plus 1. So, now we have two factors. The first factor is that as we increase the rotational quantum number, the population decreases because of the Boltzmann distribution, and you have the second factor where the degeneracy of the rotational levels keeps on increasing because of the degeneracy factor, and this is a linear relation 2j plus 1. The other is an exponential decrease, and here you have a linear increase, and the net effect is that the rotational population increases initially because of the larger effect of 2j plus 1, and then decreases because at higher values of j it is the exponential factor which becomes dominating. It is not dominating initially because
sorry to interrupt you, ma'am. We have a caller from Uttar Pradesh. Good afternoon. Please ask your question.
Yes, sir. I want to know that meanings of dipole moment.
Which one?
Dipole moment.
Dipole moment.
Dipole moment is, suppose you have two atoms which are separated by a distance, then one of them has a positive charge, the other one has a negative charge. For example, HCl, the hydrogen atom has a slightly positive charge because chlorine is more electronegative, and this charge multiplied by the distance is defined as the dipole moment. So, a molecule like nitrogen, where both have equal electronegativities, has a zero dipole moment because there will be no charge separation. So, now we were talking about two factors. One is a factor that leads to an increase in the population, and this is the first factor, and this is proportional to 2j plus 1. And the other is an exponentially decaying factor, which we saw is not very important for the initial few j values, but becomes larger for the next few values. So, initially it is the increase which is dominating, and later on it is the decrease. Whenever you have this kind of situation, it will go through a maximum, the population, and then decrease. And this is how I have shown on the right hand side picture also. The lowest energy level need not have the highest population. The highest population could be any other value of j, and by finding out dnj by dt, what you can find out is that the dn divided by dj, by taking the derivative with respect to j, you can find out that j max is equal to square root of kt by 2 hc bar minus half. You find out the nearest whole number, and that is the one which has the maximum population. Now, suppose all transitions from any level to the next level have equal probability, that means j is equal to 0 to 1 transition has the same probability as j is equal to 1 to 2 transition, and similarly for 2 to 3 transition, and so on. Then the relative intensity of line will depend upon how much is the initial population of that level. Suppose the initial population of the fifth level is maximum. In that case, when you multiply by the probability, the highest intensity will be obtained for this level. So, depending upon the j max value that you obtain, which you see is inversely proportional to the square root of b bar, you find that which is the particular line which has the maximum population. And so, this is the expression that you get. B bar values, if they are small, in that case it will be j max will have a larger value, and if they are large, it will be a smaller value. Now, linear polyatomic molecules are also ones that we can discuss here. There are examples like HCN, OCS. Remember that we had classified the molecules as linear was one of the categories. So, all these molecules HCN, OCS, CO2, they all belong to this category. So, then because they belong to the same category, so carbon dioxide out of these is microwave inactive because it does not have a dipole moment. So, the problem with this is that suppose you have a molecule like OCS, it has a dipole moment, it shows a microwave spectrum, but there is only one rotational constant, because remember that B is equal to C, and this implies that you will be able to get one rotational constant.
We have another caller. Yeah, please go ahead, ask your question. कश्मीर से हैं जी, सवाल पूछिए.
my question is tops, sir.
जी सवाल पूछिए.
Sir, my question is spherical tops.
Pardon, we are not getting your voice.
Sir, spherical tops, sir.
नहीं, आपकी आवाज नहीं आ रही है.
Sir, my question is spherical top, sir. Spherical top.
हाँ. See any molecule, हाँ.
Hello, sir. Sir, my question is spherical top, sir.
हाँ.
Spherical tops के बारे में मैम ये आप ये कुछ बताइए.
Spherical.
समझ नहीं आया मैम. जो आपने
हाँ,
पहले
मैं आपको
बताया
बताती
spherical
हूँ.
top.
Okay.
हाँ, जैसे मॉलिक्यूल लाइक मीथेन है, वो टेट्राहेड्रल शेप है. वो उसका अगर शेप देखो तो लाइक अ बॉल है, बिल्कुल. मतलब जैसे बॉल होता है, बिल्कुल सारे डायरेक्शंस में सेम होता है, लाइक अ स्फीयर बॉल जैसे होता है, क्योंकि उसके वो टेट्राहेड्रल है, पूरी सिमेट्री है. ऑक्टाहेड्रल मॉलिक्यूल है, वो भी इसी तरह का होगा, जिसकी अगर आप शेप देखोगे. फुलरीन मॉलिक्यूल है जो नैनो में आप आजकल उसके बारे में बहुत सुनते हैं. तो दीज आर ऑल स्फेरिकल टॉप्स, क्योंकि उनकी शेप बॉल की तरह है. तो इसका मतलब कोई भी डायरेक्शन उसका फेवर्ड नहीं है. ऐसे मॉलिक्यूल्स का कभी डाइपोल मोमेंट नहीं होता, क्योंकि मीथेन का आप मीथेन जैसे है, मीथेन के चारों डायरेक्शन सेम है, चारों बॉन्ड सेम है, उसका डाइपोल मोमेंट नहीं है, तो वो स्फेरिकल टॉप हो जाता है. लेकिन क्योंकि उसका डाइपोल मोमेंट नहीं है, तो यू कैन नॉट स्टडी इट इन माइक्रोवेव स्पेक्ट्रोस्कोपी. ठीक है. Okay, I'll finish this. Suppose you have,
Yeah, you continue.
If you have a molecule like OCS, there are two bond lengths to be determined, RA and RB, but you have only one moment of inertia. आपके पास you have two unknowns, but you need to find out, you have only one rotational constant from which you can determine. Now this is a problem because you need to determine two of the constants. Now how this is solved is that you take another molecule of OCS with some isotopic substitution. Instead of oxygen you can have oxygen 17, for carbon you can substitute with carbon 13 or sulfur 32 by 34, any one of these, and you get another value of B, and now you have two equations and two unknowns. You can find out both RA and RB. And for example, you don't even have to do any enrichment, क्योंकि आपका whatever is naturally available will contain some of these isotopes of oxygen, carbon, sulfur and so on, and we get bond lengths from all these data. To confirm, I mean just two unknowns and two equations is not enough. You can take a third equation and confirm that the value that you obtained is correct. So 34 sulfur is already present at 4% in natural sulfur, and without doing an additional calculation like you got for carbon monoxide, you can find out the bond lengths for these. And before I wind up, I'll briefly tell you about the Stark effect. Just like you have Zeeman effect, where the different MJ values come up at are separated when you apply a magnetic field. When you do it in an electric field, a similar kind of separation occurs, from which you can determine the dipole moment. So one of the applications of microwave spectroscopy was to find out very accurately the bond lengths. Now we are also able to find out the dipole moments, and this is one of the best methods for finding out the dipole moments. Molecules in outer space are detected using microwave spectroscopy, and many of these have been detected. I mean obviously nobody can find out what are the species which are present, which are the interstellar molecules. Microwave spectroscopy using this kind of radio telescopes has made it possible, and from these rotational lines we have detected such molecules like OHCN, CO, CS, even molecules which are not very stable, we've been able to detect. And molecules like oxygen, hydrogen, nitrogen, acetylene must be present there, but why we are not able to detect them is that they have no dipole moment, so they are not microwave active. And this is one such spectrum that we have obtained for from interstellar molecules from the Orion Nebula, and you find that there are a number of molecules which have been detected. And
sorry, we have another caller from Rajasthan. Good afternoon, please ask your question. जी सवाल पूछिए.
अमोनिया नाइट्रोमेट करने पर क्या देता है?
अमोनिया के एक्चुअली यू कैन नॉट, काफ़ी चीज़ों पे डिपेंड करता है, बट फ्रॉम द IA, IB, IC वैल्यूज इट इज़ फाउंड टू बी एन ऑब्लेट टॉप. ऑब्लेट टॉप होता है, like benzene, वो ज़्यादा उसका एंगल कम होता है. एक्चुअली वो इट इज़ अ पिरामिडल शेप, पर उसका एंगल इतना कम होता है दैट इट इज़ मोर लाइक बेंजीन, तो उसको ऑब्लेट टॉप कहा जाता है. आई नो उसके बारे में देयर इज़ अ लॉट ऑफ कन्फ्यूजन. कई बुक्स में प्रोलेट लिखा होता है, कईयों में कुछ लिखा होता है, पर अमोनिया इज़ एन ऑब्लेट टॉप मॉलिक्यूल. ठीक है. And I'll just summarize this lecture. And only polar molecules absorb or emit. Very precise measurements allow calculation of moment of inertia I. For diatomics, you can calculate precise bond lengths, and as I told you, up to the 5th or 6th place of decimal. Triatomics, you can get up to 4 unknown bond lengths, you can, or angles can be calculated. Dipole moments are accurately measured using the Stark effect, and the most important application is that interstellar gases have been detected using microwave spectroscopy. And finally, there has been talk about what books. This is one of the fundamental books which gives you a very good, not very complicated, simple book which gives you a very good picture of fundamental spectroscopy. This is by Banwell, and it is in India. It is published by Tata McGraw Hill Education. As far as I remember, the cost is between 200 and 300.
Okay. So, well, friends, I thank all of you for watching the lecture, and on behalf I thank Dr. Rita Kakkar for giving such a wonderful lecture. And tomorrow we'll have another lecture on this spectroscopy, and we'll give more time for the interaction. So you may ask question tomorrow also. Thank you.